Hello students, today we are going to discuss again the applications of uniform circular motion. In the previous lecture we have studied banking of roads and derived one relation, that is the most safe speed Vs is equal to under root Rg tan theta, with which the vehicle can be driven along banked road. For the derivation, we have used the diagram of banked road like this. This is the angle of banking. So the vehicle we have shown in this way. This is the center of gravity through which the weight is acting vertically downward. Normal reaction shown, which is perpendicular to the inclined surface. Components of normal reaction are shown: n cos theta vertical component and horizontal component is shown by n sin theta. Here n cos theta is balanced by weight. N sin theta represents resultant centripetal force, and by using such forces we have derived this speed, which is the maximum most safe speed. But practically all vehicles never travel with the safe speed. Sometimes they travel with the speed which is less than safe speed. Sometimes they travel with the speed which is greater than the safe speed. So for the sake of understanding, I draw here a number line. Suppose this is 0 of a number line, and safe speed is denoted by Vs. So the vehicles traveling with velocity less than Vs, the values are represented over here, and the values which are greater than Vs are like this. So vehicles can travel with the values less than the safe speed, but here there is a speed limit. Suppose it is shown by V1, or this speed limit can be denoted by V minimum. It is minimum possible value or lower speed limit so that vehicle remains safe. It is not most safe speed, but it is lower speed limit. It represents lower speed limit. If vehicle travels with the speed again less than V1, then it is dangerous to that vehicle. That vehicle may fall along the incline in the downward direction. Similar is the case if the vehicle travels with the speed greater than Vs. There is particular limit V2. Here I can write it is V2 like this. Here V greater than Vs, or V2 also can be denoted by Vmax. It represents the maximum speed limit, upper speed limit like this, but usually it is denoted by V2. So above which, if any vehicle takes the speed greater than this upper speed limit, then also it is dangerous to that vehicle. That vehicle may skid along the tangent. So here there are two possibilities. If speed is less than lower speed limit, it may fall or it may go in the downward direction. If the speed exceeds again the upper speed limit, then vehicle may go along the tangent. We have to derive the equations for V1 as well as V2, means lower speed limit and upper speed limit. So let us proceed further one by one. Now we consider here first the derivation for V1. So for that derivation we have to consider the force of friction, force of static friction, which can takes its limiting value or maximum value. Always its maximum value is given by mu s into n. So this force we have to consider. How can we consider it? Let us show it in the diagram. For the outer wheel of this vehicle, here the road surface and tire surface are in contact. Here we can show that force. So this force we have to show if the vehicle is moving with a speed which is less than the safe speed. Suppose its minimum value is V1, then we can show the force of friction in this direction, means in the upward direction, because the role of force of friction is that it has to keep moving the vehicle, not it avoids slipping of vehicle. So try to understand carefully here that when vehicle moves with or travels with the speed less than the safe speed, it may slip in the downward direction, but Fs is the force, it avoids the slipping of vehicle in the downward direction because it takes its limiting value or maximum value. Now how can it avoid the slipping of vehicle? For that we have to consider components of this Fs. Here components can be shown. Horizontal component is here by showing here theta is Fs cos theta, and from the same point we show the vertical component. This is a vertical component is Fs sin theta. Fs sin theta. Now we can use these components in this theory like this. Here we can write here the centripetal force mv1 square upon r. But in this case this force is less than n sin theta. This is because for the safe speed we have written mv square upon r exactly balanced by n sin theta. But in this situation this v1 is less than this v or vs. V is vs. So here this v1 is less than v, therefore mv1 square is also less than mv square upon r. So instead of writing equality here between the two forces, we have written like this: mv1 square upon r is less than n sin theta. Now we have to use this inequality by using the geometry of figure. It can be like this. So observe carefully here. Horizontal component is n sin theta. Exactly opposite horizontal component is Fs cos theta. So we can take here n sin theta, n sin theta, n sin theta minus Fs cos theta. This is the resultant centripetal force and it can be equal to mv1 square upon r. Now let us substitute for Fs. Here Fs can be substituted as mu s into n, like this, n sin theta minus mu s n and cos theta is multiplied. mv1 square upon r. Now divide this equation by n cos theta. Just for the adjustment, for further simplification, we can here divide both sides by n cos theta. We get on the right side first term divided by n cos theta, second term also divided by n cos theta here, and the equation we get mv1 square upon r is equal to, it is tan theta, and then it gets cancelled. Here also n cos theta gets cancelled. Here it is the first equation, mv1 square upon r. Here mv1 square upon r divided by n cos theta. This gives us tan theta minus mu s. Same is the case for the second component, that is, we know mg is balanced by n cos theta in our usual case, but here considering the Fs component, here n cos theta and Fs sin theta both are parallel to each other and they are balancing the weight of vehicle. So here we add Fs sin theta, and substitution for Fs gives us mu s into n and the sin theta. Here mg is equal to this equation. Again here we divide both sides by n cos theta. We get on both sides dividing with n cos theta. Here the simplification is also for the equation. Here mg upon n cos theta, it can be equal to 1 plus mu s tan theta. You can easily note the cancellation. So this one is the second equation. Now for the given situation, when the speed is less than set speed, we have two equations. So let us divide equation 1 by equation 2. We get v1 square upon rg is equal to tan theta minus mu s upon 1 plus mu s tan theta. This is the simple division. Get v1 square is equal to rg, inside the bracket tan theta minus mu s divided by 1 plus mu s into tan theta. And finally v1 is equal to under root rg, inside the bracket tan theta minus mu s divided by 1 plus mu s tan theta. So this equation is numbered as 3. So v1 is it can be denoted by minimum speed or lower speed limit, so that vehicle can go along the banked road and it remain safe. It is not the most safe speed, but it is safe speed, and it is representing the lower speed limit. Similarly, we have to consider the upper speed limit. The same treatment we have to give here, and it can be now written again on the number line. We consider it is easy to understand by using the number line here. Now the vehicle is traveling with the speed which is greater than Vs, and one particular value is V2, which is the upper speed limit. For this we have to consider the centripetal force as mv2 square upon r. Usually, if we are not considering the force of friction, it is simply equal to n sin theta. But here, as this V2 is greater than Vs, this mv2 square upon r is greater than n sin theta. So I can write it here clearly. Fv2 square upon r is greater than n sin theta. The value taken for the velocity is greater than step speed. Therefore, it is not balanced exactly by n sin theta, but it is greater than n sin theta. So, for this situation, as speed is increasing, here vehicle goes, or it has tendency to skid. So for that, the force of friction again comes into play. It takes its maximum value, Fs is equal to mu s into n, but it is in the downward direction. In this case, it can be represented here by drawing the figure. Suppose we draw here like this. Fs is shown here. It is in the downward direction because vehicle has tendency to skid along the tangent. Therefore, it keeps the vehicle on the road, moving along the road, or keeping its motion. It maintains its motion. Itself, it adjusts in the downward direction. Now, here also it can be resolved into two components. One is horizontal component. Here angle is theta. It is Fs cos theta, horizontal component, and vertical component is Fs sin theta. Now, taking into consideration with these two components, we can write again two equations here. The first equation, write for the centripetal force. The centripetal force, necessary centripetal force, can be obtained by the figure like this. Here n sin theta is towards the center, Fs cos theta is also towards the center, and both are in the same direction. So we write n sin theta plus Fs cos theta. But Fs takes the maximum value. So we can write here n sin theta plus mu s into n cos theta. This is for mv2 square upon r. Let us here say that the resultant centripetal force is n sin theta plus mu s n cos theta if speed is greater than set speed. Now, dividing this equation by n cos theta, we get mv2 square upon r. This is divided by n cos theta. Right side also divided by n cos theta. This step you can understand easily. This is the simple method to obtain the equation. Here mv2 square upon r divided by n cos theta is equal to tan theta, sin theta upon cos theta. Here mu s remains in the second term. After cancellation, this is equation, say A equation here. Now the second equation is we can consider for the vertical components is usually n cos theta is balanced by mg, but here n cos theta is opposed by this fs sin theta in this diagram, because we are considering the force of static friction. Here mg is vertically downward, n cos theta vertically upward, but it is opposed by fs sin theta. So instead of writing simply n cos theta, we write it as n cos theta minus fs sin theta. mg is equal to n cos theta minus fs can be substituted as mu s into n into sin theta. Dividing again on both sides by n cos theta, we get mg upon n cos theta is equal to n cos theta divided by n cos theta. For the second term also, divide by n cos theta, we get here mg upon n cos theta is equal to 1 minus mu s. Here n will get cancelled and the ratio is tan theta. This is equation B. Now solving A and B or dividing equation A with equation B, we get the relation like this: V2 square upon Rg is equal to tan theta plus mu s divided by 1 minus mu s tan theta. We take it in bracket. So V2 square is equal to Rg inside the bracket tan theta plus mu s divided by 1 minus mu s tan theta. So V2, which is now representing upper speed limit, it is under root of Rg tan theta plus mu s divided by 1 minus mu s tan theta. So this is suppose equation number C equation here we denote. It represents the maximum possible speed or upper speed limit with which vehicle along the bank road remains safe. But if this limit is again exceeded, then I have told it goes along the tangent. So this is about the speed limits, lower speed limit and upper speed limit. Based on these derivations, you have to attain the questions which are short answer questions. So this is about the homework. Today we will stop here, and tomorrow we consider one again application of uniform circular motion and numericals. Thank you.